Looks like we're up and running, hopefully recording. So this is lesson number 2 in a series of videos that I've decided to make. Big decision here to actually, whatever handout I give to a class, I'm actually going to do all the problems out. It's a whole different approach in teaching. And I made a few notes to myself. I wanted to say maybe how to use these videos, and the thought process behind it is, if you were to do 60 things, 1 minute a day, each of those things you just spent 1 minute, spend an hour. So you look at 60 things and each one you look at for 1 minute a day. Okay. What would happen over 60 days? Okay. 1 minute a day, 60 days. Or what happens if you did just one thing, 60 minutes each day? Right? And then went to something else the next day. So not each day, just one day. You spend 60 minutes looking at one topic. And then the next day, you spend 60 minutes looking at a new topic, and so on and so forth. At the end of those 60 days, and if you tested someone, well, who do you think would do better on the test? Well, I've actually had 2 careers, one where I taught sequentially and one where I taught holistically. And I'm telling you, I learned a lot more when I started doing this about math than I ever thought I would. And I had a class where a bunch of students, good portion of the students in the Algebra 2 level on a final exam were not able to write the equational line. And I just said, I'm done. I mean, if that's the best I can do, and my test scores were the same as my colleagues. If anything, they're a little bit better, because I did have students getting up out of their chair working at the board. So most of the time the scores were better, but it was still very disappointing. And at that point, I threw everything out the window and I said, we're just going to do it. We're going to do, everybody in this room is going to do the equational line just for a minute every day for the whole term. And since I've done that, I've never had a student not be able to write the equational line. And I have students coming in Algebra 2 all the time, and most of them don't remember how to write the equational line on day 1. And as far as I'm concerned, that means never learned it. So we've been doing it for the last 3 days, and I'm happy to say most of the kids can write the equation line pretty quickly right now. And I think 4 days in a row usually is the magic number to pick up most topics in high school math. Now we've got 14 calculations that we have to learn. We've done linear, quadratic. I gave a challenge on a square root over the weekend, which I'm going to do. And I'm going to bring up exponentials in this graph so that we start considering and start the conversation, spend a little time. But the goal here is to repetitively do it and have a conversation, repetitively do it and have a conversation, and master the material by eventually getting to the point where you can explain what you're doing to someone else. That's what the course is about. And I'm happy to have people piggyback along. Doing this mostly for the students who in class will be working on this worksheet. Got all the problems on the board. They're going to be working on it on Monday. And maybe even Tuesday, might even do the same worksheet. But we will be moving along and doing a little bit of this and a little bit of that every day. And for folks who aren't in the class, I'm sorry, you're not going to get as many conversations. You're not going to get as much work. But you can still piggyback and maybe, try this out. And I will be talking a little bit more about context and concept. Because the beauty of technology is you can move around in the video and go to different places. So what I think I'll do is show you the problems that we're going to look at. And just briefly, you can, well, that's not going to work. So what's the best way to do that? I don't know. Here, maybe you can take a screenshot. All right, maybe this can work. Maybe you can, yeah, it's right side up. Maybe you can screenshot that when I get it to stop, and then screenshot the other side. And maybe that's something that can work, or maybe somebody can write to me, right? As I say, I'm not averse to having chats. That's my email, jbollinger@nmhschool.org. Had some great chats with folks over the years who just wrote and started talking about math. One gentleman in particular, thanks, brilliant mathematician, and we've had some nice chats, and I've learned so much from him. So that's great. So where was I? Hoping that maybe that works, and if not, maybe somebody can write to me, because I'm not great with computers at all. I had a flip phone as of 2 years ago. Maybe it was three. I'm losing track of time. And yeah, I'm just starting to learn, texting the last couple of years, and yeah, it's not my cup of tea, but that's all right. So 4 days, it's how I learned math as an adult. I'd read something and I knew I was going to be teaching calculus at some point, started looking at integrals, and I shut the book in a hurry. I read something and went, I don't know what the heck is that? But then I picked it up the next day, read it again, and picked it up the next day, read it again. And by day 4, I was starting to I think I'm getting a little bit of understanding here. All right. And so that's how I approach the study of mathematics. And I think it served me well. So going to do exponentials, going to do inverse functions today to get the conversation started, and hope that we can put those in our pocket during the semester and actually know what we're looking at. All right. So if I said everything I want to say, I think so. Okay. So let's go over here. Let's put my computer on. I get it to sit nicely. Looks like it's kind of off-centered. So let's put it over here. Sorry for the delay. There, that'll work. There. Down there, nice. Yeah. Yeah, this cart's my friend. I can really move it around. So I gave it a name. Call it Rene. Yeah, Rene the cart. Sorry about that. All right, so linear quadratics are on the board. This was the challenge question I gave. And there's 14 calculations we're really going to study in this class, all the way from linear to sinusoids. And hopefully we'll mention by the end of the semester some derivatives, because I hope by then it makes sense. And I've seen students kind of march through this quite well. All right, so what was the answer to this? Well, might as well introduce inverse operations. So we've looked at quadratics. Here's a quadratic. It's a U-shaped graph. 0, 0. You're looking what direction here? You're looking this way. So 1, 1, 2, 4, 3, 9, the acceleration. But if you change the x's and the y's, you end up actually with something that looks like that. All right. And I've done dotted here. There's more conversation to have. But a square root function really looks like either the top half or the bottom half of this shape. And we could reflect it in the other direction, but that's maybe a month or two from now. All right. So that's a square root function. And what I'm suggesting is there isn't anything that we can't graph at the high school level in less than 10 seconds, except maybe rational functions. Right? We'll do those late in the term. Okay, but everything else follows a nice template. When the graphing calculators came out in late 80s, I remember seeing them go boop, 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 boop. And I said, if the machine can do that, we should be able to do that. Don't know what made me say that, but that's what I thought. And it turns out we can. And I figured that out when we started doing these problems once a day, every day. All of a sudden, patterns started emerging that pretty simple now that I think about it, but didn't seem like it at the time. So how do you do this equation? All right, so squares have area. That now area has gotten smaller. And remember, squares have square roots, lengths of sides. So now that area just got smaller. And the square roots of distance just got smaller. Just got smaller. And I could keep going until I get 0 times 0 is 0. So square roots have a minimum. And if you look at the progression, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. Bigger gaps. All right, so it takes more and more area to get 1 unit of change from a square. Okay, for the length to grow by 1 unit, it takes more and more area. Maybe deceleration is a good word for that. I don't know. Talk to the physics folks. All right. So the major operation that gives us this trajectory, square root. If I put an 8 in, I want it to act like a 0 to get me started. And if I put a 15, I get the square root of 7, which is not a friendly number. I'm going to get rid of it. Because what matches with an 8? 3. And how do I get from 3 to 5? I better add 2. That's that equation. All right, now we're going to do exponential equations. So there have always been more than 5 sheep in Gill. I don't know if you knew that, right? I'm a Gill Billy. There's always been more 5 sheep here, since thousands and thousands of years ago. Yeah. Yeah, I was in a cave then. Every 100 years, the population appears to be doubling in some way. So it doesn't seem like I can see the numbers double, but I kind of feel like they're doubling. And in 1725, I took a data. That was a good year for some folks. The herd was 16. I counted 16 sheep in the pasture, out there in the pasture. And in 1825, 100 years later, there were 27. 27. And I now looked out again because I've been around a long time. So, well, right? 2025, 93 sheep. Yeah. And I'm like, got to figure this out because I know there's a pattern. And so I just, started thinking about it. And Rene Descartes helped me out. Said, why don't you draw a picture? Show the years horizontally. Show the years horizontally. And show the population vertically. I said, okay, Rene, I can do that. And so there's always been more than 5. Well, I put a little dotted line. I said, it's like 5 feet. Still 5 feet. So, I'm shrinking though. So y equals 5. And I know my population was doubling. Well, wait a minute, I think. Double, double, double. Oh, that's even going up fast. Ooh. Oh God, well, things don't double like COVID did every 3 days. Doubling. Oh, yeah. So I think, that just decided to, go y equals 5. Well, since I got 1725, I actually have a number, 16. I know I got to go up 11 units. Get to 16. I got a marker. I can do this. And then some time elapsed. So let's just write elapsed time. Because the next number was 27. 27 minus 5 is 22. Oh, 22. And that kind of made me think that my conjecture there about doubling, something kind of doubling, seems to be taking place here. Well, let's write the equation of what we see. Right. Well, first off, all my y values, which are sheep, were more than 5. 5 plus. I asked a Waldorf student, what would be a good symbol to show that we're more than 5? Well, up arrow. I said, yeah, we could have done that. Okay, but more than 5. How much more than 5? Inquiring minds want to know. Well, I think 11. I think 11 more than 5 takes me to 16. And that happens in 1725. So, okay, all right. But of course, the course is based on zeros and ones. And so I'm thinking exponentially now. I'm thinking, well, let's put an exponent on top of a base. And let's see, can I put a 0 on that? I think 5 to the 0 is 1. I think 1/2 to the 0 is 1. And we talked about that earlier in day 1. Not going to do it again right now, but probably should. But the next time I got 22 on top of 5, which is 27 sheep, and I know that's not 11. So why don't I get rid of it? Little conversion here. Get rid of that 11 and bring in the number 22. Because 22 plus 5 takes me to 27. I think I can see the number 5. I think I can see the number 16. And I think I can see the number 27. And let's move this over, 2025. Oh God, I forgot what number it was. I guess I'll have to solve an equation to find it. Hope it comes back to whatever I wrote. Oh Lord, within the 90s, I think. But because I know b to the 0 is 1, I think I can write, how about we do t instead of x for time? No, it's a math class. X minus 1725. Let's see if I put 1725 into this I'm gonna get rid of this now, because this is now a number factory I'm creating. So let me make my factory here. And get the little smokestack and hopefully catch the carbon. Here we go, I'm dropping in 17. What was it? 1725. So I forgot the 5 there. Okay. 1725 minus 1725 is 0. Anything to the 0 is 1. 1 times 11 is 11. Plus 5 is 16. Huh. It kicked out the number 16. Let's go 100 years later. 1825. Let's kick that in there. Let's put our smokestack over here. 1825 minus 1725 is 100. 2 to 100 is 2 times 2 times 2 times. Oh, I don't like that. I just wanted to double it once. Right now it's the number 100. I don't know how to turn the number 100 into a 1. Oh yeah, I do. I got a marker. Let's divide it by 100. Wow, look at that. Now let's drop 1825. 25 minus 1725 is 100 divided by 100 is 1. And I think 22 over 11 is really 2, and 2 to the 1 is 2 times 11 is 22 plus 5 is 27. Oh my goodness. Wow. If I learned how to do that, I bet I could have done that in 10 seconds. But I forgot what that number was there. So let's put 2025 in and find out. 2025 minus 1725, I think that's 300. Divided by 100 is 3. And 2 to the 3 is 8. And 8 times 11 is 88. Plus 5 is 93. Thought it was in the 90s over here. Correct me if I'm wrong. I'm probably going to make some computational mistakes because I'm talking and I'm old. And I can't do both anymore without making mistakes. It's awful. Awful. All right, so that gets a conversation started, which means now we're going to do exponential functions, every day for the rest of the term. And I actually snuck a couple in this worksheet. So 20 minutes from now, maybe longer, we hit another exponential function and I'll give you a chance to forget everything you've seen. Then you got to try to remember it. But let's solve this equation right now. Let's actually solve this equation because I think that we can get 93. If we solve this equation for 93, it should come back to 2025. Oh, it does. 5 plus 11, 2, x minus 1725 over 100. And I want to see when it equals 93. Well, I didn't leave myself much room here, so I guess I can make one. Rene Descartes, you sticking with me here, buddy? You, Rene, there. Okay, so what am I going to do with my class? I'm going to subtract 5 from that side, and that gets me 88. I'm going to divide by 11. That gets me 8. And now I'm at 2 to the x minus 1725 and over 100. Sure looks like I'm looking for an exponent. There's a clue. What's our actual inverse operation, especially if the numbers were nasty? It's not nasty numbers here. You probably know this thing has to equal 3, right? Because 2 to the 3 is 8. Okay, then we're back to algebra 1 steps. But we're learning something new. We're learning how to isolate exponents. Yeah, and 100 years earlier, I talked to a guy who was figuring out how to do this. Yeah, his name was Napier. Yeah, spent 20 years in a castle figuring out these table values anyway, it's a nice story. And it's logs. And that's why we started with logs on day 1, because it's not the easiest thing to understand. But I hope that's easy for you now. I think everybody in the room knows what to say that answer is. And yes, it was 3. And so therefore, what do? I multiply by 100 and I add 1725. And if we do that, by golly gee, I think we get 2025. The conversation has started. Now, other conversations that have already started, I'm going to go through quickly. And if you need help, I'll give you the videos you can go look at so that you can keep pace. Linear function through -12. I'm going to write x plus 12. I want to get 70. I got a marker. I just put it down so that when I put this into this factory, -12 plus 12, there's our 0 plus 70 is 70. Now I'm going to put 3 in, and 3 plus 12 is 15. I don't think I go up 15 units to get from 70 to 2. I get rid of that 15 units. How do I get from 70 to 2? I better go down 68, and there's our equation. Play it again, Sam. All right. How do I find 4 locations on this? Well, if I learn this process, I can see that the critical number here is 7, and it gets me a 5. I think I better do it above for space. I can see the number 7 gets me a 5. And since we said that has meaning, x2 minus x1, which really is just the change in x, it's easier to say, how do I get to 7 and change by 4? Well, I think 11, 15, 19. I think I'm changing my x's by 4. Why don't I change my y's by going down 3? And let's check this factory. Let's put this factory, let's put a number in. That's a smokestack. There we go. Let's let it cook. So let's put 19 in here. Do the math. 19 minus 7. I leave it there too. It's 12. I know how many times 4 goes into 12. I got to divide that number by 4, and I got to multiply it by -3. Doesn't matter the order. Why don't I divide it first? I know all of you want to multiply it, but why don't I divide it first? I get 3. 3 times -3 is -9, and -9 plus 5 just so happens to be 4, so this actually works. Nice to know. Okay, what did I do here? I think I probably did the wrong process, so I'll let you do that one in a second. I already forgot that problem. I think I was supposed to do slope-intercept. So I'll do slope-intercept here, even though it's a whole lot harder. And I remember what this is. Yeah, I think I was supposed to do slope-intercept here. So I better do it. -3/4. Everybody loves slope-intercept so much. Plus 5. All right, so what's that equal to? Well, you got to know how to multiply fractions. So -3/4 x there. Minus times the minus is a positive 21/4. And then I got to add 5. And I trust everybody should learn how to multiply a fraction and add an integer to it. So that's -3/4 x plus 21/4 plus, I think that's 20/4. And I think slope-intercept, which is a product, so that's why we use the number 0, it's the easiest number to multiply by, will get me the quantity 41/4. Okay. Okay, that's done. All right, so now we got the same question again, but hey, you got a little repetition. Can you name 3 points, 4 points on this line? You pause in the video, I hope, each time. I'm not going to keep saying that. So every time I get to a new problem, if you want to try it, pause the video. I see 17 gets me 20. Then I see that I'm changing by 100, 117, 217, 317, and I'll go down 3, 17, 14, 11. And let's put 317 in. That gets me 300. How many times is 100 going to 300? 3. What's 3 times -3? -9 plus 20, 11. I didn't make a mistake. Let's move on. All right. Let me get a graphical approximation here. We covered that on Friday. I see -3x minus 5. I'll call that -5. Down 3/1. I got a linear function that does that. 2x plus 10. If that's 5, then 10 is up there. Up 2/1 looks like that. I better get a small negative answer for x when I do this. If I don't get a small negative answer, I'm not trusting my work. All right, so how do I want to approach this? I'll bring the minus that way. There's 5x. I'll bring the 10 this way. There's -15. I'll divide by 5, and I get a small negative number. Let's get Rene Descartes over here. Come on, Rene. Got to get by a set of desks. All right. Gonna go around the room. And if you know how to do those problems easily and well, I'm gonna bring Rene over here. Come on, Rene. Okay, I'm almost ready to come back. Got to make a space on the table. All right, here we go. Okay, next question. How do we solve a problem like that? Well, in our class, we're just gonna get the first line of work eventually, but right now we'll check things out. Let's just get a feel whether we got a correct answer. One more repetition won't hurt us. Down 7, down 2, over 5. So something that looks like that. And 7x over 3, so I'm at -10. If this was -7, -10 is pretty close, probably there. I'm gonna go over 3 and up 7. Over 3, up 7. Okay, so I get an intersection, near 0 but positive. So I got a near 0 but positive intersection. So let's get rid of these fractions. Let's get rid of division by 5 and 3. Why don't I multiply by 5 times 3? 15, because I know 5 goes into 15 3 times, and that becomes -6x. 15 times 7 plus 35, I believe, is -105. Hope I'm not making any mistakes. 3 into 15, 5 times 7, 35x. And 15 times -10, -150. I don't like to divide by negatives, so I'll bring that over. That's 41x. I'll bring the 150 over, so that should be positive 45. And I get an x value that is small, near 0, positive. I think I'm okay. All right, so now we're gonna, I don't know what I was supposed to push it through, but I say, let's get an equational line, passes through the point high there and perpendicular to that. So there's a pattern here, so there's no need for work. There's no need for work, and I want to get high. No, sorry, didn't mean to say that. I school here, I'm not advocating. I want to put high into the parentheses. What's there? Okay, don't want to mislead any youngsters here in the wrong direction in life. Whew. Yeah, so high minus high is 0. I don't think I'll use high again. Gets me there. Yep, putting in high gets me there. God almighty. Then you ask, how did I know how to do that without any work? Well, let's solve the problem. Perpendiculars are negative reciprocals, right? We can draw that pretty quickly. Over 2 up 1. That look like 2 to 1. Okay, perpendicular is actually over 1 and down 2. So they're reciprocal relationships and opposites. So we got to find the slope. Well, how do we find the slope? I don't like dividing by negatives, so I'll bring the 14y this way. I'll bring the 400 this way. Then I'll leave the 15x here. And I get a slope of 15 over 14. What's the negative reciprocal? Negative 14 over 15. And so it's always good to put your answer. So perpendicular to this is my answer was y equals negative 14 over 15 times x minus I plus there. It's always good to take your answer and look at the original and take a moment. Okay, maybe you're seeing a pattern. Be nice. All right, so number factory, right? This is the number factory. What do we do with number factories? We plug numbers in, and I think on the worksheet it was, so I got the worksheet in my hand. Without my glasses on, can I still see it? What number are we on? 7? F of 5. So what that means to do is to plug 5 in for x. I think it would be easier if I did it here. 5 sevenths, there's x means Arabic for the word something. And that something right now is a 5. So I'm going to use that 5. That's the something I'm going to use, -2. Now, I think it's really important to know how to do fractions quickly. All right, a little repetition from a moment ago. We need a common denominator, and I think 7 times 2 is 14 over 7. Oh, I think I can do this now. I think my number factory kicks out. Plugging in the number 5 into the factory, go to work, I think I get -39 cents. A little bit smaller than -5. Oh, f of x equals 10. Well, that means I get 10 out from my number factor. I got to figure out what I put in. Well, I think we can do the inverse. And when you evaluate, you go hard to easy. Inverse solving, you go easy to hard. So let's take the easiest operation, move it to the other side. It's gone. Let's take that operation, move it to the other side. 7 times 12 is 84. I just did 7 times 12 in my head that way. Okay. And then divide by -5 gives me an answer of x equals -84 divided by 5. Always move the negative into the numerator. All right, we're going to do it every day. I have no doubts we'll be fine with that in time. So we'll just take it on a daily basis. And I bet you it won't take you too long to feel comfortable with that. All right, 2 to the x equals 1 over 32. Well, 1 over 32 is 2 times 2 times 2 times 2 times 2. I'd like you to know that. So what's the answer that gets you that? -5. I'm doing it 5 times, right? 2 to the 5 gets me 32. It's in the denominator. We talked about that on day 1. Right? That takes a fraction and flips it. So I'm really doing 1/2 5 times. Half times a half times a half times a half times a half is 1 over 32. All right. We'll be practicing that along. Square root of 200. Yeah, this is actually a little bit new. I'm hoping it isn't. I'm hoping you had it in your Algebra 1 class. All right, but let's look at square roots. Properties of square roots. And the easiest one to look at. Let's start with 2 times 3 equals 6. And 2 is the square root of 4, and 3 is the square root of 9, and 6 is the square root of 36. I think there's something to learn there. Okay, so it still bothers me, but a square root times the square root is not squaring. Seems like it is, but it's not, because the numbers inside are not the same. Right, so a square root times a square root yields a square root. And what's inside times what's inside yields what's inside. And so it's nice if you know the squares. If you know 1, 4, 9, 16, so on and so forth. Maybe to 100. Because I know the square root of 200 is the square root of 100 times the square root of 2. And so I think I can call that number something else. I think I can call that number 10. Root 2. And I'm asking my students to memorize a whole bunch of things, especially square root of 2. And I'm saying, let's use the number 1.41 and memorize it. Write it down. Look at it every day for 2 seconds every day, 10 days in a row. You'll remember it. All right, so if I multiply that by 10, square root of 200, it's pretty close to 14.1, just as a little feel for size. Okay, that was nice to know. Why do I see this? Because I'm giving you every problem that I see kids butcher in a calculus class. I see kids write 5 plus 5. Let's do 6 plus 4 divided by 4. 6 plus 4 divided by 4 does not equal 6. Okay. Division does not undo addition. All right. 10 divided by 4 is not 6. 6 plus 4 divided by 4 is, however, 6 over 4 plus 4 over 4. That is a true statement. So I'm dividing this into both parts. And I want to make sure that if you go to a calculus class, you're not the person who says that goes in a certain number of times and writes 21x minus 114. All right, so that is equal to 21x over 5 minus 70 over 5. And it's important that you know that. All right, so what's the square root of 11 times the square root of 22? Well, it's actually the square root of 11, and I can rename that. I can rename that as the square root of 11 times the square root of 2 based on something we just talked about 3 minutes ago. This I know. I know the square root of 11 times the square root of 11. Just the same way that I know what the square root of 9 times the square root of 9 is. And remember, you can pause the video at any time. Anytime when I say something, and I just got to do this because, I've got another 20 problems to do here. And it's going to take some time, so I can't talk forever here. Right? But square root of 9 times the square root of 9 is 9. So I wonder what the square root of 11 times the square root of 11 is. It sure looks like the square root of 11 is being squared, and now we have inverse operations. I think it's 11. So I think this thing could have been written as 11 root 2. Useful skill. Let's go, Rene Descartes. Okay. So m to the 12th over m to the 4. is 12 m's, 1, 2, 3, divided by 4 m's. 4 of them cancel out of the problem to become the number 1. And so the rule here is 12 minus 4, or m to the 8. From your Algebra 1 class, you should already know that. Okay, now let me get another marker, something that works nicely, I hope. Let's see, give me a break. No. Uh-oh. Uh-oh, marker dying. Next time I'll have 2 markers ready. Let's see if I can find something here. This one doesn't work. I might have to change a cartridge. Oh, we're home free. That'll get us there. All right. New problem. X minus 2 times what gets me x squared minus 8x plus 1. All right, in Algebra 1, you probably did long division. You might have even done synthetic division. I don't know. But it's easier to do these problems, most of them, in your head. Okay, you're never going to see anything in probably calculus class that's much more difficult than that. And the reason I'm giving this problem is in calculus, people can't integrate x squared minus 8x plus 1 over x minus 2 easily. Folks have trouble with that. Okay, and this practice will make it so you don't have trouble. It's going to take you a while. This probably takes more than 4 days for a lot of you. Okay, and let's do it out for the first time. Remember, the first stage of learning is following. So you just simply try to follow what I'm doing. And it'll take your brain a while for it to be able to do it easily. I think I get started that way. Yay! And I've done enough foiling that I know x minus 2 gets me a middle term of minus 8x if I put a minus 6 there. Right? But let me do it out a little slower. X times x is x squared. Minus 2 times x is minus 2x. But I need minus 8x. So I need to get another 6 in that direction, in the negative direction. And it comes from that FOILing process. That gets me minus 6x. Now I've got to get the number 1. Right now, minus 2 times minus 6 is positive 12. I got to go down 11. But now I'm in trouble because that gets me minus 11. That's really troublesome. I wish I didn't have to multiply that minus 11 by x minus 2. And I don't have to multiply it by x minus 2 if I put x minus 2 below the 11. Magic. Amazing what you can do with a marker. All right, so let's hide this a little bit. You do that multiplication right there, and you see x squared minus 8x plus 12. Okay, so we did that multiplication. Let's do this multiplication. Minus 11 over x minus 2. What happens when I multiply that times that? I hope you see that. And now I get minus 11. That gets me 1. And I know some of you are shaking your head right now going, oh my God, you were shaking your head when we did the equation of a line on day 1. Right? And I don't hear anybody complaining after 3 days of practice. So give yourself time to learn how to do that. I'll give you plenty of time. All right. Patience. A lot of mathematics requires patience. Yeah, I'm a very patient guy. All right. Oh, sorry. Oh, new notation. Okay, you're used to seeing this in class now. 7 to the negative 1, which is 1 over 7. This does not mean that. This means I'm going to do this. That symbol means I'm going to do this. So I go from to No, I got to go backwards. I went that way. Yeah, it's the inverse. A lot of calculations have a lot of operations. And we're pretending the inverses. And where do we use inverses? I don't know why I said pretending. Where do we use inverses? It's solving all equations. So what would happen if I wanted to solve this equation for some number? 2x minus 3 equals some number n. And this works for most inverse problems. Most inverse problems, you can simply pretend you got a number and try to solve. All right, so what's the inverse of minus 3? Adding 3. What's the inverse of multiplication by 2? Dividing by 2. And now we have 2 functions. Change that to x. We won't say equals, but they're inverses. How do we check? We use a number. Let's use 10. Let's put 10 into this number factory, and if you're paying attention to it, you get 17 out. And what's the inverse of 10 to 17? 17 to 10. 17 plus 320 divided by 2, 10. I wonder what the inverse of exponentiating is. Oh, that's right. We did it before a half hour ago. Logs. Yeah, it's a long video. I hope you're going through it in whatever way you want. All right. Vertex of a quadratic, -2, 7. Well, that means I got to do x plus 2 squared plus 7. That's the vertex. And that's got to be true because squares have a smallest area when the side length is 0. So that's got to act like a 0. So x plus 2 squared. I can't get anything smaller than 0 squared. Quadratics have minimums. Minus sign in front of parentheses makes it a maximum. Okay, so I'm throwing a lot of things in your head. And then what happens when I put number 10 into the number factory? Well, this is a constant. So the number factory here, there's 2 factories. Now that's the one that we're using first. What happens when you put a 10 in there? 10 plus 2 is 12, and 12 squared is 144. So I'm going to go up 144 units to get from 7 to 6. Oh, Rene Descartes told me that's wrong. So I better get rid of that 144 units of change because it doesn't work. How do I get from 7 to 6? Down 1. I think you can learn that 2 or 3 weeks from now. Most of you will do that in under 10 seconds. It's not much different than the equation of a line, except instead of rise over run, it's rise over run squared. Why? Because we're squaring. So we have to get rid of squared units of change. Imagine that. Triangle 3 times that symbol. I wish I could speak Greek. I did meet Pythagoras. He was a friend many centuries ago. Nice guy. He was a good guy. So I think that might be a Greek letter, but what do I know? All I know is if I want to turn a 3 into that, what do I have to multiply by 3 to get that? Well, I don't see the number 3 over here, so why don't we get rid of it? It's gone. If I want to see that, why don't I write it in? That'll be fun watching students look at that problem on Monday. I won't be posting this. This is Saturday. Snowing out. For you in warm climates across the globe here. Here, have a little look-see at some snow coming down. It's a good thing. Yeah, nice little picture out there. Not much sun today, obviously, but maybe it'll clear up. We'll see. So I'm here now. What's a logarithm? Can you just answer it at this stage? Can you just see that it's -2? You got to take a reciprocal and square. Reciprocal and square, that's a language. That's what that exponent is telling me. It's telling me that if I put that number on top of 1/3, it's going to come out as a 9. We've looked at why. I'm not going to spend time here. But I could do this out. I could do 1/3 to the x equals 9. That's what this is asking me to figure out. And I do know that 3 to the -1 is 1/3. And I know 9 is 3 squared. And I know -1 times x is -x equals 2. So I guess x is -2. I could have done it out analytically. All right. Not going to spend time on factoring x squared minus 10x plus 21. It's x minus 3 times x minus 7. You've already had an Algebra 1 class. We'll figure out where you're at there as we go along. How do I graph 3x squared minus 12x minus 7? Well, I know it's cup shape up. I know minus means I'm on the decreasing, read graphs from left to right. My finger goes down. That tells me which side of the cup I'm on. 0, -7. I explained that in the quadratics playlist. So go there if you want to get an explanation as to why. You certainly could have done minus b over 2a first to get that x value. So minus b, 12 over 6, 2. And 2 is to the right of 0. So you could have done this one first, then figured that out. And if I put a 2 in, we should see the 2 to 1 ratio. Minus 24 means that should be 12 without looking. And you do the hardest operation first. You square it before you multiply. Evolution of the discipline. All right. And then you subtract 7. And if you do that out, you get minus 12, minus 7, minus 19. And if you want to know where that 3 came from, ask yourself, how do you get from negative 19 to negative 7, up 12? And what's the quadratic change from 0 to 2? From 0 to 2 or 2 to 0, it doesn't matter. What's the quadratic change? That's linear change. The quadratic is 4 units of area. What do you get when you divide 12 units of area by 4 units of area, multiplication of 3? Not sure I wanted to say area there, but I did. All right, so that's how you do that problem. You do what's hardest first. I hope that you pay attention to your foiling process. I never do this out anymore. I never have to do that. I just look at that and say x squared minus 6x plus 9. Got enough practice to be able to do it. You do that out, see if you can figure out the pattern, how you could get it without having to do it out. I'm multiplying that by minus 10, and then I'm adding 12 last. That's an operation that isn't written. It's understood to be plus 12. Okay, and so what's my final answer? On the side, let's just do it here. Minus 10x squared, minus times the minus plus, oops, forgot the square. Minus times the minus plus 60x. I got minus 90 plus 12 is minus 78. I believe that's correct. Okay, 5x minus 2y is 30. You just graphed that for the first time yesterday, I believe, maybe Thursday, I forget. We haven't done it much, but we've done it a couple of times. And can you already know how to graph that? It's in standard form. All right, so how do you find the graph if it's written in standard form? X and Y intercepts. Okay, an x-intercept means the y value is 0, a y-intercept means the x value is 0. You'll hear me say that the whole semester. So you cover up 1, and I can see x is 6. So over here, a 6 gets me 0. And if I cover that up, y is negative 15. Negative 15 might be much further down, obviously, if that's 6. So there's my line, whereas 0 gets me negative 15, right? Because these are products. Right? And you can always learn something by making the product 0. In every context, critical numbers just start coming at you. Okay. And I hope you understand that if you have a constant, if one number goes up, right? If I want 30, I can get 31 minus 1 to get 30. And if I make it 32, I can do minus 2 to get 30. That x and that y, that operation, right? That just got bigger, 1 got bigger, 30, 1 got bigger, and it's still 30. Okay, so each number gets bigger as my x gets bigger, my y's get bigger, as my x gets bigger, my y's get bigger. So a subtraction in a standard form means you have an increasing line, and an addition obviously means you got a decreasing. It doesn't hurt to know that. Wow, I hope you're going through this video where you need work. So I'm going to look at 3a, I'm going to get a little harder factoring problem A. And now, whatever number I put there, it's 3 bigger than you think it is. So if I put the number 1 in, it's really 3 now. And 3 and 8, right? Because 1 times 8 is 8. 3 and 8 don't give me 10. So let's put a 2 in there. And now I got a 4. 2 becomes a 6. And 2 times 4, 6 and 4. Ah, subtraction. And I can't, 1's got to be negative. Shucks. How about a 4 tripled is a 12? And 4 times 2 is 8, and 12 and 2. Ooh, so I want 4 and 2 here. I want 4 and 2. So I can make this one 4. 4 times 3 is 12. Minus 2 is 10. So that's what it was. And the more you do it, the better you get. You don't have to take so much time. You can just kind of Rolodex it through your brain. Got to get practice. All right, so we did this on Friday. Don't know if you remember it, but again, I like to give you at least 4 days of, looking at something for a minute a day. And I hope you can see that x could equal 0, or x could equal negative 99 over 203, or x could equal 1 over 52. Let's put 1 over 52 in every x location. So I got 52 over 1 divided by 52. I got 52, 1 over 52, and I got 1 over 52 And that's 3/52, that's 203/32 plus. Oh my God, that's a tough one. Oh, look here. Oh, 52's cancel and 1 minus 1 is 0. Oh, so length times width times height equals volume. And if I make my height equals 0, I got no volume anymore. Wow. Jeez. Okay, we'll do that every day. I'm not worried about us learning that. 2 months from now, do that once a day. 5 seconds and answer. Okay, so if I was doing this test, if I was doing this worksheet out, given the number of years I've been doing this, I don't have to write much out anymore. Probably 10 minutes, something like that. And I hope you get there too. So what do I see here? Another graph, quadratic. I see cup shape down. And I know I'm on the decreasing side. So, but we'll get the minus b over 2a and the y value at minus b over 2a. And then you can see that the y-intercept is on that side, decreasing side. So minus b, 24 over 2 times that, -8. That gets me -3. So I want to write, so -3, so I can just do that, -3. Right now, I hope you can see that I was correct, that 0 is to the right, and that's -8. The only thing you got to do is plug -3 in. And if we do that, we'll plug it in. So if I was doing it, probably do it here, -36, right? -3 squared is 9, right? Which means that this is going to be twice that in opposite. So I probably would have done it that way, or cut that in half and then put the 3 in. But anyway, the shortcut is 36 minus 8 gets us what? 28. Okay, I hope that's right. I hope I didn't make a careless mistake. But I think before I run out of battery on the computer, I better keep on going. So f of x equals 2x plus 3, and I wanted the y-intercept. Whenever you want a y-intercept, throw 0 into the number factory. And I'm saying this again because I want you to know what 2 to the 0 is. I'm hoping you stop saying 0. 2 to the 0, anything to the 0 is 1. 1 plus 3 is 4. So the y-intercept is 0, 4. Okay, very quickly again. 1, 2, 3, that's m to the 3. Now it's m to the 2. Now it's m to the 1. Now it's m to the 0. And when you divide something by itself, you get 1. Okay, it didn't take me long to do that. F of g of 10 means that we're going to drop 10 into the g function. We're going to do it out, and then we're going to drop it into the result after putting 10 into the f function. It's called a composite. This is called a composite. Okay? And on your SATs, it'll probably come to you in this form, f of g of 10. I prefer this form. My rule is whatever I have to do less of, rotator cuff problems. So my marker, 1, 2, 3, 4, 5, 6, 7, 8 strokes of the pen of the marker. 1, 2, 3, 4, 5, 6, 7, 8, 9 on the right. Took me more. I think it's simpler to write it that way. But you'll see it that way. And it's read f of g of 10. So what is g of 10? G of 10 is 100. What's f of 100? Tells me to cube it. That's 6 zeros. 1, 2, 3, 4, 5, 6. Sure looks like a million. Looks like $1 million. Okay, what's the inverse of f? Oh, that's what that asks, right? What's the inverse? That's what it's asking for. What's the inverse of x cubed? Just have the cube root of x. 2 cubed is 8. The cube root of 8 is 2. Just a quick check. All right, moving right along. We're almost done. Imagine when we get to 120 problems on a worksheet. Whoa, then I'm not going to talk at all. I'm just going to do it. All right, so what do I see? I see I want to make a 0 out of 5, geometric reasons why. So there's the vertex. How do you get from 7 to 11? You go up 4. What's the quadratic change from 5 to 8? 9 units. That's that graph. What are the roots? Well, I don't need any problem with the roots. I know I'm not going to use the number 5 to get to a 0. Roots are when this thing equals 0, right? And I think to get from 7, I don't think I can. I think 0, oh geez, did I butcher that? 0 is not between 7 and 11. 0 is here. I got imaginary roots. I got imaginary roots, and to get from 7 to 0, I got to change 7 units. And if I got an A value of 4/9, I better divide by 4/9. So that's actually 63 over 4. And I know the square root of 4 is 2, so I'll just do the square root of 63 over 2. Imagine that, an imaginary. Do you think it really works? Well, let's find out. 4/9. And let's plug in the x value of 5 plus minus the square root of 63 over 2. All right, let's do it. What happens to the 5s? They cancel. When you square, what do we get when we square that? 63 over 4. What happens to the 4s? Did I make a sign error? Oh, imaginary. Remember, I had the imaginary there. What happens to the 4s? They cancel. How many times is 9 going to 63? And this becomes a square, right? How many times is 9 going to 7? And so what is 7i squared plus 7? We just started talking about I squared, so that changes that. Oh, yeah, that answer is just fine. It only took 2 seconds. Vertex and the A value. We'll be doing that a lot. That probably shook you a little bit, but remember, patience, 4 days of practice, and I'll probably lecture on imaginary soon, give you a little feel for it. All right, so I said every high school function that I've been working with, you can write in 10 seconds or less. So what's this equation? Pause the video. I'm just going to do it. I see 4. From 4 to 7, I see a jump of 3. The next time it won't be a jump of 3. That's called a differential. And that's where the exponential bases come from. How do I get from 4 to 12? I got to go with 8. So that's my base. And if I want to make 1975 0, I can do it. There's 1975. Anything to the 0 is 1. 1 times 3 is 3 plus 4. Gets me 7. And how many years elapsed from 1975? I think 50 years. It's 2025 now. 50 years. And so now when I put 2000 in, I'll check it. 2000 minus 1975 is 50. Let's put 50 there. 50 divided by 50 is 1. Let's put a 1 there. Anything to 1 is itself. 3's canceled. 4 plus 8 is 12. And I've got exponential growth. The next value would be whatever 8 times 8/3 is. That's what you would get in the year 2050. Another 50 years, you'd get that amount. Going into the future, you'd get division by 8/3 going into the past. So sketch the inverse. Oh, all right, we'll sketch the inverse. That's not hard. I know the inverse of y equals 4 is x equals 4. And I know that the inverse of growth looks like that. We're doing a logarithm. My God, your first look at a log. You can write log equations in 10 seconds or less. What's the inverse of 1975 to 7? 7 to 1975. Geez, how much did my x's change from 4 to 7? Not up 3, sideways 3. Oh, Lord. And over here, how do we get from, where the heck am I? 2000 to 12? We're going to go from 12 to 2000. I wonder how you get from 4 to 12. Oh, 8. Wow, that's something. So why don't I write this equation just for the fun of it? So what do I see? I see 1975. I didn't write 1975. I did now. I see 1975. I see how I get to 2000. I go up 50. I recognize that logarithmic pattern. Good old Mr. Napier, 1600s, I think. I have to go back and check. Okay, and I know that, we've always had more than 4 sheep. So I better talk about that over here. So let's do x minus 4 because, that more than 4 sheep means that 4 is undefined right now. Because I said more than 4. Dotted line, more than 4. Okay. Let's put 7 in. Let's put 7 in. 7 minus 4 is 3. Anybody know log 3? That's a common log. 10 to the what exponent equals 3? Only Mr. Napier knew that. Thanks, Mr. Napier. I don't know it. I got no clue what that is. Sorry. You know what? I know log 1 though. I know what log 1 is. I don't care what the base is. You put a 0 on any base, you get 1s. I know that exponent is a 0. So I'm going to change that 3 into a 1 because I got a marker. So now when I put 7 in, I get log base 1, which is 0. 0 times anything is 0. I get 1975. Hooray. Of course, I got to use the next number too, which is 12. And 12 minus 4 is 8. Anybody know log 8/3? I know. But if I make it base 8/3, I know the exponent you put on 8/3 to get 8/3, it's a 1. I'll make the base 8/3. Now I got that equation. And I'm talking to you, so it took me a long time to do it. It's too bad. Would have just done it in 5 seconds otherwise. All right, so where do we start on day 1 and how are students doing with this problem? A lot better. Because people are starting to recognize that the first operation is 16 over 1. Then I've done that operation. Then it would be easiest to take the 4th root of 16, because a lot of people now know that that's 2. The 4th root of 16 is 2, so that would have been nice. And that would have been that operation, and 2 to the 3 is 8. Right, so what is minus 3/4? Reciprocation, 16, 4th root, 2, and 2 cubed, 8. Okay, so here's my friend Pythagoras. We're going to find this value. Right, how are we going to do it? We're going to look at what Pythagoras said. Pythagoras said the square area, those have to add up to this square area. Well, there you go. 9 and 25 is 34, but we're looking for that length. And that length is by definition a square root. And knowing how to do that quickly and understanding where it comes from, it's going to lead into a lot of topics. So we want to get good at it. Because we're going to be using that a lot. Oh, where am I? Almost done. Oh my God, I'm almost done. Finding distance. How do you find distance? From 1 to, let's call this 1, 2 to 7, 5. Well, from 1 to 7, I think I have to go over 6 units to get to 7, right? To get to that number. And that number doesn't get me 2. So I got to change my altitude from 2 to 5. I got to go up 3 units. Oh, so from there to there, and I want to find this distance. Geez, I wonder how I could do that. Yeah, I hope you're saying 36. I hope you're saying 9. I hope you're saying 45. And I hope you're saying, oh, that distance is the square root of 45. And since we did it earlier, we might as well get a little. Can you simplify that? Maybe you're pausing the video here. I hope you're saying the square root of 9 times the square root of 5. I'm hoping you're saying 3 root 5. And I do not know what the square root of 5 is. Don't use it in trig too much, so. Okay. What the heck did I ask here? So I got a function. Maybe I asked to graph it. Right? That would be an awful one to graph for you folks at this stage. Okay. Oh, no, I'm here anyway. So good. I don't have to worry about that next problem. And I got another 6 problems here to do. So what's this asking you to do? To find the exponent on top of 1/2. Oh, I have the exponent to get x. Oh, so to get that x value, I have to use the exponent. And I hope from our previous problem, you see that as 1/16. All right, so what the heck am I doing with this problem? That's a nasty problem to ask you for 2 coordinates. Should I really do this? That's a tough one. I know the square root of 3 is root 3 times root 3. Right, so that cancels. So I really have the same thing as root 3, which is kind of like the mx plus b form of a line. But I definitely know that a square root function has that shape. We talked about that at the beginning, and the square roots, the smallest a distance can be in a square is 0, because 0 times 0 is 0. So I got 1 is the minimum, getting 9. And then I gotta find a way to get, let's go back to 3 over root 3. Sure would be nice if that was root 3. Well, I guess I could make it root 3 by saying 1 plus root 3. Yeah, 1 plus root 3. If I put 1 plus root 3 in here, and I subtract 1, I get root 3. And root 3's cancel, and I get 3 plus 9 is 12. So I guess I could graph it, but I don't think I should do it for you because it's kind of a tough one to start with. So pretend I never did it. Would you like to do an easier one like we did at the beginning of the class? Would you like to try now? 6, 7 to 1920. That was a very good year, 1920. Got a lot of friends in it. Yeah. I partied up too much in that decade, and a lot of people get in a little trouble in the stock market. It's a tough time too. Anyway, square root of x minus 6 plus 7. Throw a 6 in, throw a 19 in. 19 gets me the square root of 13, which I don't think plus 7 takes me to 20, but 13 does. Well, that must be something Freudian going on here. Let's make this a 21. So we go up one more. Yeah. Otherwise, starting to feel a little strange. All right. So, exponential function when the data comes your way. So let's do it again. So y equals 2. That's the asymptote. I got to get to 11. Guess I got to go up 9. Next time I'm not going to go from 2 to 19. Well, I think that's up 17. Right? I got to make a 0 out of 1910. And 1910 to 1930, 20 years of change. Put that into a grapher, you're going to get an exponential function that goes through those 2 points. And it's almost doubling, 17 over 9. 18 over 9 is doubling. So I got an exponential function that's not quite doubling in that direction. We're cutting in half in this direction. Sure looks like one of those problems to me. Don't panic. First 3 weeks of my classes, it's like Navy SEALs. It's a tough time, training camp. Then it gets easier. Maybe it gets harder for them. All right, subtract 4. This is what I'm hoping I see. Subtract 4 gets me a 12. Divide by 3 gets me a 4. The inverse of logging base 2 is exponentiating base 2. And the inverse of subtraction 5 is adding 5. 16 and 5 should get me 21. Let's see if it works. Let's put 21 in. 21 minus 5, 16. What's the exponent you put on top of the 2 to get a 16? 4. What's 3 times 4? 12. 12 plus 4, 16. Let's move on. What are the roots? Well, I can see the roots here easily. What hits a 0? I can see that easily. 4 plus or minus square root of 5 over 3. I got to make that inside the square root. Yeah, didn't have to do any work there. Oh, how did I know that? Well, let's put it in graphing form. 3 x minus 4 squared minus 5. Let's set it to 0. You tell me what happens. Well, you got to go up 5 units. That's over here, right? And if you're multiplying by 3, you got to divide by 3. If you're squaring, you got to do plus minus square root. And if you're subtracting 4, well, you got to add 4. Let's put our answer in, see if it works again. We did that once before. 5, which doesn't work. 5 does not. 4, sorry. What did I say? Oh, yeah, it's over here correctly. 4 doesn't work. 4 gets me negative 5, so we got to get rid of that number. We got to figure out how to change. How to change. This thing has to equal 5 because 5 minus 5. So we got to get there. We got to get a 5 in here, right? But multiplication by 3's got to get canceled. And squaring's got to get canceled. Plus minus square root. So what happens to the 4's? We did a nice job of cancellation. Plus minus times plus minus. Always positive. What happens when you square a square root? You get what's inside. What happens to the 3's when you divide by 3? They cancel, and 5 minus 5 gets us our roots. Then the quadratic formula, give me the vertex and the a value, and that's a 3-second question once you practice it enough. Will you get enough practice? Yeah, it's on tomorrow's worksheet. It's on the one after that. It's on every test the rest of the year. Got to have working knowledge with math. Otherwise, you don't go into the next class remembering what you took from the previous class. And there's no way that you can do calculus. It's not possible. You don't have the foundation. Okay. X squared minus 5x plus 4. Well, not all equations get solved with inverse operations. Sometimes it's easier to just write it as a product. And if one of these parentheses can be made into a 0, then we have truth, justice, and I don't know where we are, but that kind of way. So what two numbers multiply out to be positive 4 and add up to negative 5? We can do that provided the coefficient is a 1. So I can do that here, and I can see minus 4 minus 1. They multiply out to be the last term, and they add up in the FOILing process. So what do we have? We have a parabola. At 4, we get a 0, and at 1, we get a 0. 1, we get a 0, and at 4, we get a 0. I see that, which means that my b over 2a should be 5/2. That's the number in between, because minus b over 2a is the average of the roots, and I will be explaining that in the upcoming days more thoroughly, geometrically why. Okay? And so 5/2 minus 1 is 3/2. 3/2 squared is 9/4. If I'm not mistaken, that should be minus 9/4. But you can plug it in and play with it and see. Now, I have changed the last few problems to easier numbers than what are on that worksheet. So I'm going to go with the easier numbers. So remember, this is asking for the exponential activity that gets created in this bracket. So I got an m to the 6th over m to the 2, which becomes m to the 4. I'm doing that 5 times, so I have 20 m's as factors. And now, can I figure out what I put on top of m to get m to the 20th? I hope you say the number 20. All right? And I've been forgetting to put brackets on, which means I've been making a mistake for years. Right? I need to have all of this in the argument of that function. So 2 times 4, the exponential activity is an 8. 4x squared plus 8 equals 24. I'm not going to use factoring here. I'm not going to use the quadratic formula. I have an isolated x with 3 operations. Those 3 operations, I should be able to do inverse operations. I'll take 8 away from 24. That's 16. I'll divide by 4. That's 4. And I'll take the plus minus square root of 4. And that should get me 2 or negative 2 for answer. So let's put negative 2 in. What's negative 2 squared? 4 times 4, 16 plus 8, 24. I showed you I squared briefly Friday. It's the number times itself that gets us negative 1. You hear the word square, you're squaring. Comes from geometry. And this is the square root of negative 1 times the square root of negative 1. And mathematicians, 1500s, 1600s, started looking at this and trying to get answers for questions like x squared equals 9. X squared equals 9 at 3 and negative 3. Well, what happens if we want x squared equaling negative 9? Well, we need to reflect the graph in the other direction. And it turns out it matches up with the same magnitude, except that we've done something that requires a little communication. And so I like to see the y-axis really as the flipping. Right? And I'm starting to play with that with the cubic. I think there's reason to think that you can visualize it that way, but not done thinking about that. All right, this is the longest video I've ever made, but I am going to do it because I think that as someone who wants to really take the time to learn the math has the opportunity to as we go through this semester. And from class, you can go anywhere and, you use that slider. I don't know what to call it, you go to the problems that you're having trouble with. We'll keep talking about the others because you can keep talking about this stuff forever. I mean, I've been working with graphing formula cubic since the late 90s, and it wasn't until last year that I completed the cube geometrically. I'm embarrassed it took me that long. Okay, but I don't think it's out there. So the more you look at things and the more you keep looking at them, the stuff keeps getting interesting. Never stops being interesting. So I'm rambling on big time here. Okay. Hope it helps somebody. Ta-ta.